Everybody. So today we are discussing one of the bond parameter, bond angle. The bond is characterized with three parameters, that is bond angle, bond length, bond energy. So now let us focus on bond angle. So how do we define the bond angle? Bond angle, it is the angle between the two adjacent bonds bonded to a single atom in a covalent molecule. We call it as the bond angle. And what are the factors that influence the bond angle? The first factor is the electronegativity of central atom. For this, we are taking the set of fifth group hydrides, ammonia to bismuthine. In ammonia, nitrogen is more electronegative. So the entire lone pair density, bonded pair density is concentrated on nitrogen. In bismuthine, bismuth is less electronegative. So only lone pair is concentrated on bismuth. Bonded pairs, they are more close towards hydrogen. So what is happening here? Nitrogen is smaller in size and moreover it has more electron density. So the repulsions exist between the electron densities and that is going to increase the bond angle. To minimize the repulsions, the bonds have to move away, which is going to increase the bond angle. In bismuthine, of course bismuth is larger in size and it has less electron density. Only lone pair is more concentrated on bismuth, bonded pair is more concentrated towards hydrogen. So less electron density on bismuth, less repulsions, less bond angle. That is what we are summarizing here. Electronegativity of central atom, if it is increasing, electron density on central atom increase, repulsions increase, bond angle increases. So we can say that electronegativity of central atom is directly proportional to bond angle. So as you move from ammonia to bismuthine, electronegativity of central atom is decreasing, bond angle decreases, which you can observe in their values. Similarly, water to hydrogen polonide. These are also in the same group. From oxygen to polonium, electronegativity of central atom is decreasing, therefore the bond angles decrease. Now the second factor, electronegativity of surrounding atom. For this we are taking the example of water and oxygen difluoride. So what happens? In water molecule, if you take water molecule, oxygen is more electronegative. So the lone pair density, bonded pair density is concentrated more on oxygen. And if you take oxygen difluoride, fluorine is more electronegative. Therefore, bonded electron pair is concentrated more on fluorine. Oxygen, it has more amount of lone pair density. So when you compare the oxygen atoms in water and OF2, oxygen atom is in water has more electron density due to less electronegativity of hydrogen. So more electron density, more repulsions, more bond angle. Now when you move to oxygen difluoride, fluorine is more electronegative than hydrogen. So bonded electron pair is concentrated on fluorine, only lone pair is concentrated on oxygen. So less electron density on oxygen, less repulsion, less bond angle. So how to summarize that? We say that if electronegativity of surrounding atom increase, electron density on central atom is decreasing, as we see in OH2 and OF2. Electron density on central atom decrease, repulsions decrease, bond angle decrease. So that is electronegativity of surrounding atom is inversely proportional to bond angle. So in the other examples also, we can see the same effect. Ammonia NF3. So fluorine is more electronegative, therefore the bond angle is less, 1 or 2 degrees. And as you move from the trihalides of phosphorus, phosphorus trifluoride to phosphorus triiodide, electronegativity of surrounding atom, that is from fluorine to iodine, is decreasing, therefore the bond angles are increasing. Electronegativity of surrounding atom inversely proportional to bond angle. The third factor is bond multiplicity. So how do we exactly define bond multiplicity? Number of bonds between the atoms in a molecule. We call it as bond multiplicity. So what is the effect of bond multiplicity on bond angle? So when we take the double bonds or triple bonds, these bonds are formed by the lateral overlap of orbitals. Double or triple bonds, they are formed by the lateral overlap. So double or triple bonds, they occupy more space, therefore they readily produce more repulsions on the adjacent single bonds. Pi bonds, they are formed by the lateral overlap of orbitals. They require more space, therefore they produce repulsions on the adjacent single bonds. So to minimize these repulsions, single bonds move away from the multiple bonds. So initially your bonds are like this. So now due to more repulsions, single bonds move away, and that is going to increase the bond angle. So we say that bond multiplicity, it is directly proportional to bond angle. So if you see the order of repulsions, triple bond offers more repulsions than double bond than single bond. This is order of repulsion according to Vesper theory. Now when you see the examples, if I take phosphine and phosphorus trifluoride, according to the concept of electronegativity, phosphine, due to less electronegativity of hydrogen, should have more bond angle. But PF3, phosphorus trifluoride, is having more bond angle than phosphine. So this is the expected order according to electronegativity, and this is observed order. Now why phosphorus trifluoride is having more bond angle? That is because of back bond. So how this back bond is formed? Fluorine, it has 3 lone pairs of electrons. And to minimize this repulsions between lone pairs, fluorine transfers one of its lone pair of electrons to the vacant d orbital of phosphorus. So we have the back bond between the p orbital of fluorine to the d orbital of phosphorus. And this bond is nothing but pi bond. Means at the place of single bond, now we get the double bond. So as the number of bonds increase, repulsions increase, bond angle increases. So in PF3, the higher bond angle is because of back bond between the p pi orbital of fluorine to the d pi orbital of phosphorus. Similarly, we can see the other example. Water, oxygen dichloride, oxygen difluoride. According to the concept of electronegativity, it should decrease from water to oxygen difluoride. The bond angle should decrease from water to oxygen difluoride. But when you see the observed order, oxygen dichloride is having greater bond angle. And the water and oxygen difluoride, they follow the normal concept of electronegativity because they don't have any vacant orbitals. But in oxygen dichloride, oxygen is having lone pair of electrons in the p orbital chlorine has vacant d orbital, back bond exists between the oxygen lone pair and d orbital of chlorine. So that is back bond between oxygen p pi orbital to chlorine d pi orbital. Again, at the place of single bond, we get the double bond, therefore the bond angle is increasing. Then how to identify whether a given molecule has back bond or not? In general, back bond is observed when nitrogen or oxygen or fluorine. Nitrogen generally carries 1 lone pair, oxygen 2 lone pairs, fluorine 3 lone pairs. When they are bonded to the third period element, silicon or phosphorus or sulfur or chlorine, which have vacant d orbitals, the back bond will exist. And whenever there is back bond, naturally the bond angle increases. Now, when we see the fourth factor, number of lone pairs or odd electron. So what is lone pair? The non-bonding electron pair present on the central atom. Odd electron, it is a single electron present on the central atom which does not involve in bonding. So if you see the order of repulsions, according to Vesper theory, lone pair has more repulsions than odd electron, lone pair more than bond pair, odd electron produce more repulsions than bond pair. Lone pair repulsions are stronger than lone pair bond pair repulsions, stronger than bond pair repulsions. For this, let us take the set of examples: methane, ammonia, water. In methane, there are 4 bond pairs, 0 lone pairs. Ammonia, 3 bond pairs, 1 lone pair. Water, 2 bond pairs, 2 lone pairs. So what is happening to bond angle? It is decreasing from 109 degrees 28 minutes to 104.5 degrees. So why this bond angle is decreasing? As the number of lone pairs increase, bond angle decrease. So how can you explain that? That is, in ammonia, nitrogen is having 1 lone pair, and lone pair, it is always attracted by a single nucleus. So the lone pair will experience more repulsions since the magnitude of attractions are less. So they try to occupy the maximum free space available on the central atom. They try to occupy the maximum free space. Due to this process, they come in close contact with bonded pairs. And at this point, we have the lone pair bond pair repulsions. Lone pair bond pair repulsions. And to minimize that lone pair, here we have the lone pair. Lone pair is producing repulsions on the bond pair. And to minimize the repulsions, bonded pairs, they have to come close. And that is decreasing the bond angle. So this is all because the lone pair is under the influence of a single nucleus. So in ammonia, the bond angle is decreasing because the lone pair bond pair repulsions are becoming stronger than the bond pair repulsions. Now, when we take water molecule, oxygen in water molecule, it is having 2 lone pairs. 2 lone pairs and 2 bonded pairs. So first we'll have the repulsions between 2 lone pairs, that is lone pair repulsion, and since these offer strong repulsions, the lone pairs try to move away from each other. So due to this process, they come close to the bonded pairs. And here we'll again have the lone pair bond pair repulsions. And to minimize this lone pair bond pair repulsions, bond pairs come close, and that is further decreasing the bond angle. So in water, the decrease in bond angle is due to the lone pair repulsions stronger than lone pair bond pair repulsions stronger than bond pair repulsion. So NO2 plus, NO2, NO2 minus. In NO2 plus, we have only the bonded pairs. So the molecule is linear, bond angle is 180 degrees. And in NO2, at the place of positive charge in NO2 plus, we have an odd electron. And this odd electron is also attracted by only the nucleus of nitrogen. So it can offer repulsions on the bonded pairs. So here we have odd electron bond pair repulsions. And to minimize these repulsions, bonded pairs come close to each other. So here the decrease in bond angle in NO2 is because of odd electron bond pair repulsions which are stronger than bond pair repulsions. Now, when we come to NO2 minus, in NO2 minus, at the place of odd electron, we have lone pair. And lone pair always produce more repulsions than odd electron. So now, this lone pair is producing repulsions on bonded pair. So here we have lone pair, bond pair repulsions. And to minimize this, the bonded pairs come close and bond angle decreases. In NO2 minus, the decrease in bond angle is because of lone pair bond pair repulsions which are stronger than bond pair repulsions. On the whole, we can summarize that the number of lone pairs or odd electron, they are always inversely proportional to bond angle. So number of lone pairs or odd electron inversely proportional to bond angle. And the last factor is percentage S character in hybrid orbital. So when the percentage S character in the hybrid orbital increase, the orientation of hybrid orbitals will change. Orientation of hybrid orbitals change and that is going to increase the bond angle. If you take sp3 hybridization, it is 25% S character and the bond angle is 109 degrees 28 minutes. In ethane, in ethylene, it is sp2 hybridization, 33.3% S, bond angle is 120 degrees. In acetylene, it is sp hybridization, 50% S and the bond angle is 180 degrees. Means what we can conclude that as the percentage S character increase, bond angle is increasing. So percentage S character in hybrid orbital directly proportional to bond angle. Now let us work out the examples based on this. So these are all the previous year questions. So we are going to discuss the answers for them. First one, trimethylamine, trisilylamine. Among these two, which is having more bond angle? So here in trimethylamine, nitrogen has one lone pair of electron, but carbon there is no vacant orbital, no scope of back bond. But if you take trisilylamine, in trisilylamine, silicon is the third period element with vacant d orbital. Nitrogen is having lone pair. So this lone pair is transferred to the vacant d orbital of silicon. So the back bond, here the back bond exists between p pi orbital of nitrogen to the d pi orbital of silicon. And wherever there is back bond, bond angle increases. So trisilylamine has more bond angle. Or I can say that the bond angle in trisilylamine is greater than trimethylamine. And the second one, that is dimethyl ether, disilyl ether. Oxygen is having 2 lone pairs, but carbon there is no vacant orbital, no back bond. In dicylyl ether, silicon is the third period element having vacant d orbital. So the lone pair of electrons from oxygen transfer to the vacant d orbital of silicon. Again we have the back bond. Back bond between oxygen p pi orbital to silicon d pi orbital. So when the back bond exists, bond angle increases. So dicylyl ether has more bond angle, and the angle of dicylyl ether is more than dimethyl ether. Next, methyl isothiocyanate and silyl isothiocyanate. Among these two, which has more bond angle? Again the same case. Nitrogen is having lone pair but no vacant orbital with carbon, no back bond. Here nitrogen has lone pair, silicon vacant d orbital, so back bond. Back bond exists between nitrogen p pi orbital to silicon d pi orbital, increases bond angle. So it is silyl isothiocyanate which has greater bond angle. And the next one, water dimethyl ether. In both of them there is no scope of back bond. But which will have more bond angle? That is dimethyl ether, because of steric repulsions. Around oxygen, which is the smaller atom, we have 2 bulky methyl groups. And these bulky methyl groups are going to cause steric crowding around oxygen, produce the repulsions which would increase the bond angle. So in dimethyl ether, the increase in bond angle is not because of back bond, but it is because of steric effects. So dimethyl ether has more bond angle. Now, you are asked to arrange this species in the decreasing order of bond angle. So how to do them? You have to see which factor is applicable over here. So if you see the first set, in ammonium, the lone pairs are 0, ammonia 1 lone pair, amide ion 2 lone pairs. And the number of lone pairs inversely proportional to bond angle. Therefore, ammonium NH4 plus has more bond angle than ammonia than amide ion NH2 minus. Now, NO2 plus 0 lone pairs, NO2 minus 1 lone pair, NO3 minus 0 lone pairs. So which will have more bond angle? It is NO2 plus more than NO3 minus more than NO2 minus, because NO2 plus, it is the linear molecule, it is having more bond angle 180 degrees. NO3 minus, it is trigonal planar molecule. There are no lone pairs here, but since it is trigonal planar, the bond angle is 120 degrees. Now NO2 minus, already we have discussed the effect there. Because of 1 lone pair, bond angle is decreasing to 115 degrees. NO2 plus more than NO3 minus more than NO2 minus. Next, BF3, PH3, NH3, NF3. BF3, it is trigonal planar molecule and all the others are pyramidal. So trigonal planar, more bond angle of 120 degrees. Now, among nitrogen and phosphorus, nitrogen is more electronegative. So more electronegative central atom, more bond angle. Means we should consider first the nitrogen series. And in this also ammonia and NF3. Among ammonia and NF3, fluorine is more electronegative and electronegativity of surrounding atom inversely proportional to bond angle. Therefore, first it is BF3, then it is ammonia due to less electronegativity of hydrogen, and NF3, and then it is PH3. Now, SOF2, thionyl fluoride, thionyl chloride, thionyl bromide. So, what is the only changing factor? Electronegativity of surrounding atom. From fluoride to iodide, fluoride to bromide, electronegativity of surrounding atom is decreasing. So, bond angle increases. So, thionyl bromide, more bond angle than thionyl chloride, more than thionyl fluoride. Now, the trihalides of antimony. Antimony trichloride, antimony tribromide, antimony triiodide. Again, the changing factor is the electronegativity of surrounding atom inversely proportional to bond angle. Therefore, it is triiodide, more bond angle than tribromide, more bond angle than trichloride. Now, NCl3 to SbCl3, nitrogen trichloride to antimony trichloride. So, in this the changing factor is the central atom. And as you move from nitrogen to antimony, electronegativity of central atom is decreasing. And electronegativity of central atom directly proportional to bond angle. Therefore, the bond angle decreases from nitrogen trichloride to antimony trichloride. Now, oxygen difluoride, sulfur difluoride. The changing factor is central atom. So, oxygen is more electronegative, more bond angle. Now, oxygen dichloride, sulfur dichloride. Again, the changing factor is electronegativity of central atom. Oxygen is more electronegative, so it has oxygen dichloride has more bond angle than sulfur